Good morning. We are headed into an entire new part of the course today. We're starting out with chapter 17. We've completed 16 chapters so far this semester. I know, it's kind of like a blur, right? We have looked at a lot of stuff, but we've completed all of the part of the course that's considered mechanics. So all that stuff about forces and rotation and oscillations and kinematics, it's all considered to be dynamics, or mechanics is the name that it goes by. And now we're headed into thermodynamics, and it's going to have quite a different feel to it. I'm guessing a number of you, usually in the 3A, 3B classes, quite a few of the students have a background because of their majors in thermodynamics already, and that's fine. And some people won't have that same background, but that's okay. We're gonna cover everything that needs to be covered, and we're gonna introduce it from the ground up. So the first chapter we're gonna look at here, and again, it's 4 chapters left, 4 weeks left. I want to say we're slowing down the pace a bit, but anyway, chapter 17. We're going to go in and talk a little bit about what we mean by temperature. What does it we mean when we say, oh, what's the temperature today? And then we're also going to talk, along with temperature, we're going to talk about thermal energy. And thermal energy is going to be a major focus of these 4 chapters. And by thermal energy, what we mean is, if we look at the air in the room, the air molecules, how much energy do they have? When I look at any object, here's a textbook, how much energy do the molecules inside here have? And we're going to find out that we have ways to understand just how much energy is present, and then we can use our ideas of energy conservation to keep track of how that energy is stored in those molecules. So a lot of really useful, really interesting stuff. Temperature, we understand to be kind of a measure of how much energy there is, and we'll see what the connection is between temperature and thermal energy. So let's go ahead and get started. First of all, one of the features of moving on into thermodynamics is we have to start talking about atoms and molecules. Now, we didn't really do that very much. Very, very occasionally during those first 16 chapters did we have examples and homework problems where we were looking at an individual atom or a molecule. But now it's going to be just really basic to everything we're talking about. Because the idea of thermal energy or heat is that just comes down to molecular motion, molecular kinetic energies and molecular potential energies. Now, to do that, we want to talk a little bit about atoms and molecules. When we're measuring samples, up until now, those samples were usually measured in kilograms or maybe grams, but we need something that tells us what the mass is for an individual atom or molecule. What's the mass of a nitrogen molecule in the air, and how much energy does it have? So we have these units, atomic mass units, that tell us that are useful for measuring masses of really tiny mass objects, atoms and molecules. And it turns out that we've defined atomic mass units so that, first of all, they're related to grams. We'll see how they're related to grams right there. And then an atomic mass unit, very roughly, is the mass of an individual proton and neutron. Now, it turns out that nuclei are a little more complicated. We can't just talk about how many protons and neutrons and add up their masses, because there is a nuclear binding energy that actually alters the mass of a nucleus. So I can't just count up the protons and neutrons from that determine the mass of a nucleus. It doesn't work that way. So what we do is we pick one particular atom, and we designate that to represent the atomic mass unit. And it used to be, interestingly enough, it used to be oxygen-16, the isotope of oxygen, that was set exactly at 16, and then, what was it, 50, 60 years ago or something, they switched over to carbon-12. So everything is based on the mass of carbon-12 as a reference. And we've set the mass of the isotope carbon-12 to be exactly 12 atomic mass units. Now, what that says is there's some different conversions going on. By that definition, one atomic mass unit would be 1.6605 something 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 10 to the minus 27 kilograms. Now, turning that around, so this is handy, this conversion totally works, but there's another way to look at this. If we take that number and flip it around, what we find is it's saying that 1 gram is equal to 6.022 10 to the 23 atomic mass units. Anybody recognize that number? 6.022 10 to the 23rd? That's Avogadro's number. So that tells us how many atoms or how many molecules are in what we call 1 mole. And we'll talk a little bit about 1 mole. Now, that's the conversion of grams into atomic mass units. If we switch over to kilograms, which we're going to use also very frequently, grams and kilograms will both get used a lot here, that's going to go up by a factor of 1,000. But I did want to write this out in terms of grams so you could see Avogadro's number show up. That's a number that we're going to see more. Now, when we think about materials around us and the types of energy they could have, there are solids. The solids we've been saying are non-compressible. The nuclei of the atoms or molecules, the nuclei are locked into some kind of a pattern. So what that says is the chemical bonding that's taking place in a solid works in a fashion where the nuclei are locked into place, and then the remaining space is filled with all those electrons. And those electrons are in different quantum states, and that's something we'll see in Physics 3b. So we'll see how electrons fill the remaining space, and how for a solid, the pattern of that chemical bonding, the pattern of the electrons, locks the nuclei into a certain pattern. Now, as temperatures go up for a solid, we'll find that thermal expansion takes place. So within that lattice, the nuclei actually oscillate back and forth, and that's what the thermal energy of a solid, that's one of the components of the thermal energy for a solid. So for a solid, the nuclei, again, are vibrating back and forth within the remaining kind of background of electrons. Okay. Now, what happens when we go from, so this could be, well, it's not ice, it's not the right pattern. This could be sodium chloride or something. Anyway, this is a solid, and this now has melted into a liquid. So what's happened? And now there's more kinetic energy. So before, there was kinetic energy of these nuclei, but now there's enough kinetic energy available that the atoms themselves, or the molecules themselves, have now gone into liquid form. So as a liquid, there's enough kinetic energy that the individual atoms can overcome the binding energy that was locking them into a crystal structure. So now there's enough kinetic energy around, the kinetic energy has gone up, the temperature has gone up, that now the molecules can move past each other. Now, liquids are still non-compressible. At an even higher temperature, we could have vaporization take place, where these, let's say these are water molecules, just because it's such a familiar, water is so useful when we're thinking in terms of thermodynamics, because we're so familiar with water going from a solid state to a liquid state to a vapor state. So here is, let's say, a bunch of water molecules. As the temperature goes up, that means more and more kinetic energy. And there's a lot of attractive force here, which we say is a potential energy locking this into place. There's less attraction here, and so it's not locked into place, but there's still an adhesion between the molecules. And here the kinetic energy dominates. So instead of the potential energy, it's the kinetic energy that dominates, and the molecules just take off at vaporization. And at that point, they're fairly independent of each other. The potential energy effects kind of go away. Now, so we've listed this. We said energy is going to be the focus of what we're looking at with these different molecular systems. There's going to be kinetic energy of translation, rotation, and vibration. Now, here we don't see energy of translation. Those things are locked in place. Here the molecules start moving. That's translational kinetic energy. And here there's a lot of translational kinetic energy once we've vaporized. What about rotations? Well, again, these are locked into place. Those molecules are not free to rotate back and forth, but here they can. So the liquid molecules will have rotational kinetic energy, and the vapor molecules also. So, you know, if you think of the nitrogen and the oxygen molecules in the air, those are diatomic. The chemical formulas are N2 and O2, and they can have rotational energies. They've got a center of mass, they've got a couple of nuclei away from the center of mass. They have rotational energy states, rotational quantum energy states. Vibration has to do with, in the simplest cases, has to do with a motion of the nuclei back and forth around the chemical bond. And so vibrational energy is very important for the solids. So the solids don't really have translation or rotation, but the nuclei can still vibrate back and forth within the surrounding electrons that are kind of locking them in place. So we definitely have vibration here. And then also in the liquid and the vapor states, you can have the nuclei, again, within the individual molecules now, you can have the nuclei vibrating back and forth. So that's oscillatory motion, and that's kinetic energy. So we've got those types of kinetic energies. Now the potential energies that we deal with here with atoms and molecules are pretty much entirely electric-magnetic effects. Now we haven't looked at that yet. We won't look at electric and magnetic forces in detail until physics 3b. So for now, let's just leave it at the protons are positively charged, the electrons are negatively charged, and there's an attraction between the protons and the electrons within individual molecules, but that doesn't completely take care of all the attractions and repulsions. So not only are the electrons being held together to the nuclei, but there's kind of this leftover effect where molecules will clump together because of those residual attractive forces. So that's why in the vapor state, the kinetic energy is so large that the molecules are moving fast enough that those attractive forces are overwhelmed. But when we lower the temperature, when we remove energy, those leftover attractive forces, you know, in the case of water, first produce a liquid, and then if the temperature drops even more, those attractive forces are able to lock the molecules in place. So it's this balance, or it's this effect of kinetic energies versus potential energies. Potential energies are trying to draw the molecules together and hold them in a pattern, whereas the kinetic energies are headed towards just random motion. Now, I included nuclear potential energies. That really doesn't come into place until we start looking within the nucleus, and that's holding the protons and neutrons together. And there's nothing in these chapters in thermodynamics where we're going to be looking at nuclear potential energies, but again, we will in physics 3b. So in physics 3b, we get to come back, take a look at the nucleus, and determine how much energy, how much binding energy there is between the protons and neutrons. So it's all done with protons, neutrons, and electrons, right? All right, let's take a look. Here's a good example to start off with. What we're going to be looking at is the in a piece of a solid, copper in this case, we're going to say copper has a measured density of 8.9 10 to the 3 kilograms per meter cubed, and each copper atom individually has a mass of roughly 63 atomic mass units. Now the 63 atomic mass units tells me that copper the nucleus of copper must have 63 protons and neutrons combined. That number would be 63. That's what will give us 63 atomic mass units. Estimate the distance between the centers of neighboring copper atoms within the crystal structure. All right, here we go, copper. So first thing I want to point out is what they've stated is misleading. Copper actually consists of two different isotopes. There are two prominent stable isotopes of copper. So naturally occurring copper is mostly, what is it, like 80% or something, copper 63, but there's like 15-20% that's copper 65. And so it's not true that each copper atom has a mass of 63. Some of those copper atoms have a mass of 65. So the 65s are mixed in with the 63s. In any case, copper is copper because it has 29 protons. So the number of protons determine which element it is and what chemical properties it will have. So a copper atom will always have 29 protons. And then it can have a variable number of neutrons. Having different numbers of neutrons doesn't affect the chemical properties. So it's still copper, even if there's a variable number of neutrons. I want to be clear about the isotope, because when we start looking at individual molecules, an individual molecule is not, or an individual atom is not the average of copper 63 or 65. It's one or the other. It's not going to be some combination of those. So if I have a large collection of copper atoms, then we can average over the properties of the individual isotopes. But when we're talking about individual atoms, copper 63 is distinct from copper 65. All right, I'm not sure what the crystal structure is on copper, but the simplest crystal structure I could think of would just be to say, let's just guess that they're cubic. Now, if they're cubic, then each atom will have a volume that's a cube, and that can be written as L to the third power, where L is the length of each side on the cube. Now, what L would also represent is the distance from one nucleus to the next, and that's what they're asking us to solve for. They're kind of asking us how big, how much space does one atom take up. So cubes are easy to figure with. V is equal to L to the third. Now, I looked up the density. The density I looked up online said 8.96 grams, so I'm going to go with that. 8.96 grams per cubic centimeter. Now, there's what's called a molar mass. A mole of copper atoms would be this number. So we just designate that for macroscopic samples of something, you know, one you could measure in the lab, we invent this number that we call 1 mole, 6.022, 10 to the 23 atoms of copper, and it's going to, 80% are going to be that isotope and 20% of the other, whatever that ratio is. But if I take 1 mole of naturally occurring copper atoms, we find that that is 63.55 grams per mole. And that's referred to as being the molar mass, and that's something I'm going to state a lot. I'm going to try to point to that, and the textbook supports all that, but I'm going to make a special emphasis because of the importance. Now, I can figure the volume by doing this. I can start piecing together the density information and the molar. This came off the periodic table, so I just look at a periodic table to find out what the molar mass will be, and that will be averaged over the isotopes. So I took the density number. Now, I wanted the volume, so I put the centimeters cubed in the numerator. I took that number, flipped it over, and said 1 cubic centimeter is the equivalent of 8.96 grams for a sample of copper. And then I wanted to cancel out the grams, so I put the 63.55 grams divided by moles. And then I wanted to get rid of the moles, so I said 1 mole is the same thing as 6.022 10 to the 23 atoms. So at this point in the calculation, I have the volume, and the moles will cancel out, the grams will cancel out. The volume will be in cubic centimeters per atom. And that's what we want. How much volume is there per atom? Now, centimeters seemed big to me, so I went ahead and did a conversion down into picometers. Picometers are 10 to the minus 12 meters, and picometers are handy to measure atoms and molecules. It turns out that's a good unit to kind of characterize the size of the atoms and molecules. Now, centimeters are 10 to the minus 2 meters. Picometers are 10 to the minus 12. And so I ended up with 10 to the 10th picometers is equivalent to a centimeter, and then I cubed it. Because there's 3 factors of centimeters, I need 3 factors of that conversion number. When I did that and carried out the calculation, it said the volume for each atom would be 1.18 10 to the 7 cubic picometers. Now that's a lot of cubic picometers, but remember, we're going after L. So L will be the cube root of V, and that worked out to be 227 picometers. And that's a sensible number. That's how big atoms are. So if I've got a molecule, or if I have a metal structure of some sort, some lattice, that's a typical distance between nuclei within a molecule or a solid. So 227 picometers sounds perfectly reasonable, and that gets referred to as the internuclear distance. All right. So, a little background with atoms and molecules here. So let's move on and talk a bit about temperature. Now, this I thought was just a little bit hilarious in these slides that the textbook put together. Temperature, it says, is a measure of how hot or cold. So I had to put the question marks in there. So let's think about that. What does hot or cold mean? I mean, that's some kind of a subjective, experiential property. I want to say this. Temperature is a measure of the average kinetic energy of the molecules, hot or cold. What I always ask students to do once we hit thermodynamics is to try to go for a week and not use the words hot or cold, because they're so vague. What does hot and cold mean anyway? Well, it means if you touch it, it feels hot, or if you touch it, it feels cold. So, when parents are telling their kids, don't touch the cooktop, don't touch the range top because it's hot. I mean, what does that mean to the kid? You got to explain to the kid what's going on. So instead of hot and cold, you would say, hey, don't touch the stovetop, don't touch the range top, because the molecules there have a lot of vibrational kinetic energy. And with that vibrational kinetic energy, when you contact it, vibrational kinetic energy can transfer from those molecules and atoms into the molecules and atoms of you, and that could damage some of your tissue. A little vibrational energy feels good in your hands and whatever, but if you get too much vibrational energy, it could take apart some of your molecules and it could cause damage. So that's the sensible thing that you would tell a kid, right? Don't say because it's hot. You got to say be careful because there's a lot of molecular motion there, and if you touch it, that molecular motion will transfer into you. Same thing with cold, right? It doesn't have much molecular motion. If you contact that, it could end up that some of your molecular motion, the kinetic energy associated with that, transfers into the cold object, and your molecules won't have as much molecular motion. And to be comfortable, you want a certain balance of molecular motion in the molecules that make you up. And our neural system is set up so that if we don't have enough molecular motion, we feel cold. And if we do have too much molecular motion, it feels hot. And so those become signals to us that we need to move to a location where the ambient molecular motion is higher or lower. Hot and cold. Ha. Okay, so practice that. See if you can do it. That's the challenge. Can you go a week without using the word hot and cold? Instead, talk about molecular motion every time you have an inclination to say something hot or something is cold. Instead, talk about the molecular motion. Okay? Drive your friends crazy. That's what this course requires. All right, so here are some temperature scales. I'm guessing you guys are familiar with these, probably all of them. You guys know about Fahrenheit. And you guys know about Celsius. Now, the Fahrenheit and the Celsius scales are both set up in a way where the degrees, each degree Celsius or each degree Fahrenheit, are set up in a linear fashion related proportionally to the amount of translational kinetic energy in the molecules. Okay, so that's important to begin with, is how do you, once you've identified, let's see, Celsius, at 0 Celsius, water freezes at 0 Celsius. At 100 Celsius, it vaporizes. But how do you put the units in between that? That's maybe not entirely clear. How do we make sure that the spacing is uniform between 0 and 100 Celsius? What would that even mean? And what we can do is we can use, we'll look at an example here. We can use what we consider to be an ideal gas model. Gas molecules are a good way to do this, and show that as the temperature goes up, those gas molecules have more kinetic energy. And we'll see that we can set a temperature scale where the temperature is directly proportional to the amount of kinetic energy in an ideal gas. All right. Anyway, that's how the scales are set up. Now, Fahrenheit is set up at 32 at freezing and at 212 with vaporization of water. Originally, the Fahrenheit scale, 0 on the Fahrenheit scale, was the temperature at which saturated salt water would freeze. So the intention with the Fahrenheit scale was we can get lower than freezing water. We can dump a bunch of salt in, and then the water will freeze at an even lower temperature. And then the original idea with Fahrenheit is 100 would be body temperature. But anyway, in the course, we're going to be using Celsius. We're really not going to be using Fahrenheit. But even more than Celsius, we're going to be using Kelvin. So I put Kelvin in really big letters there. Celsius is kind of misleading, because when I hit 0 Celsius, I would think that would indicate there's no energy left in the molecules. That's not true. At 0 Celsius, there's plenty of energy left in the molecules. Just because it's ice and it's a solid doesn't mean the energy's all gone. All those nuclei inside the water molecules are vibrating back and forth. There's vibrational kinetic energy in a block of ice. So what we can do is go, okay, what would it take to remove all of the kinetic energy? And it turns out on the Celsius scale, we can show experimentally, we have to go all the way to negative 273 Celsius to remove all the kinetic energy. So what we've done with Kelvin then is start at the point where there's no kinetic energy left. We call that absolute 0. Absolute 0 means we're not kidding around this time. 0 really means 0. Kelvin's is the only one of these temperature scales where 0 really means 0. Kelvin means what it says. Celsius and Fahrenheit, they're not serious. When they say it's 0, it's not really 0. So anyway, we start at absolute 0 and set that to be 0 kelvins. And that says by the time we get to 0 Celsius, we're already at 273 kelvins. By the time we get to 100 Celsius, we're at 373. So kelvins is, kelvins are the units to use here. So when my friend and I, my friend from way back from early elementary school, when we got to high school and took chemistry and learned about the Kelvin scale, we made a promise right there that we would never use any other temperature scale again. Kelvins was so cool. Okay, it didn't last very long because practically we were in our chemistry class, we were working in Celsius all the time, and we couldn't stop to convert to kelvins every time that happened. But anyway, that's the idea, is ultimately kelvins is the true temperature scale. All right, here are the conversions between these. So there are ways to switch back and forth between Fahrenheit and Kelvin. These are the formulas, and Fahrenheit and Celsius and Kelvin. And the one we're going to be using the most here is conversions back and forth between kelvins and Celsius. And that just means adding or subtracting 273. Now it turns out it's actually 273.15. Most of the time we'll leave that out. I'm always a little worried that we are not including that, but we're showing that right here. Now, body temperature, for example, we're told is 98.6 Fahrenheit. Using these formulas, we can show that that works out to be 37.0 Celsius, and turns out to be 310 kelvins. So I always want to get thermometers, right? You go to the doctors and you get a thermometer and they check your temperature and they go, oh, your temperature is 98.6. And you go, I don't want that in Fahrenheit. And they go, okay, it's 37 Celsius. And you go, no, kelvins. I want the units in kelvins. So we need a thermometer that is in kelvins so we can go, oh, you're fine, you're 310 kelvins. All right. Here is just a quick statement of the, what we find is that there is this idea of thermal equilibrium, meaning that when I put a bunch of materials in contact with each other and I allow the thermal energy to transfer back and forth, statistically what happens is that the energy distributes itself in, it's not a completely random fashion, but it's the statistically most likely way. Now when that happens, then we say that all of the components of the system are in thermal equilibrium because on average the thermal energy transfers now balance out. And we say that when things reach thermal equilibrium, they are at the same temperature. So it's kind of interesting that we can actually derive mathematical formulas telling us how the energy is distributed between the molecules using statistics, choosing an approach called statistical mechanics. All right, we're going to move on to a different topic here. We're going to move on to thermal expansion. Now, thermal expansion says when the temperature goes up, there is going to be, what that indicates is more kinetic energy within the material. Let's say this is a piece of steel or maybe a piece of aluminum, something like that, some metal structure. As the temperature goes up, that indicates to us that more energy is present in those molecules, and what we find is more vibrational energy of the nuclei actually leads to a larger separation between them. As the nuclei vibrate back and forth with more energy, the equilibrium point in terms of nuclear separation goes up. So every nucleus moves away from every other nucleus just a little bit, and that results in what we call thermal expansion. Okay, so that happens throughout the material. And not only is this going to get longer in this direction, the diameter is going to increase by the same proportion. So if we get a 1% effect, which is quite a bit, a 1% effect of thermal expansion along the length, then the diameter also goes up by 1%. The formula that we represent that with says that at the higher temperature, the length will be equal to the length that we had back at some reference temperature, and usually the reference temperature is 20 Celsius. And then this extra piece represents the fractional increase. So the fractional increase in terms of the length, it depends on the material. So different materials have different fractional increases. When that vibrational energy goes up within those, let's say we're looking at a solid piece of some metal, when that vibrational energy goes up, the new equilibrium distance is different for different materials. So alpha is referred to as the coefficient. Now they call it linear expansion. I think that's a bad name. I think we should call it the coefficient of thermal expansion. So this is the linear coefficient of thermal expansion, or the coefficient of linear thermal expansion. Now when we say linear, it means we're only looking in one dimension. Now, as we said, this certainly applies in all three dimensions, but often we can set the problem up so we can just look at one dimension, and that's all we need to look at, and it will tell us what's going on in the other dimensions. So in this case, the length in whatever dimension we decide to measure it will be the original reference length times 1 plus some sort of a fractional increase. That's going to depend on the material, and it's going to depend on how much the temperature increases. And that is why that's actually why we call it linear. Okay, so the linear thermal expansion assumes that as the temperature goes up, the length will increase proportionally to that temperature. Now here are the expansion coefficients, alpha, and we'll see, aluminum is like 25 parts per million per Celsius. Steel is another common one we look at, 12 parts per million. So you can see that these metals are seeing, 15, 20, 25, 30, something in that range parts per million. Glass is kind of interesting because look, glass expansion is much smaller. Glass does not expand so much as the temperature goes up. Quartz, very, very little. So it's kind of interesting. Now, there's a whole column of these one-dimensional linear expansions. And there's also a column of what we call volume expansions. Now, the formulas work the very same way. We take out the lengths and put in volumes instead. Now, it turns out that because these are small effects, going to 3 dimensions actually just results in multiplying the number by 3. You can see all through here, that's just 3 times the number in the alpha column, the number in the beta column, showing how much the volume goes up. It goes up in 3 dimensions, and because that amount is so small, that roughly approximates out to just multiplying by a factor of 3. The volume increase, if if the length increase is 1%, the volume increase will be 3%. Okay, and we can think of that of 1% in each of the 3 dimensions. Now for liquids, this is interesting too. For liquids, the one-dimensional expansion doesn't make sense because it doesn't have a definite shape. But for liquids, we can definitely have a volume expansion. So for liquids, that's kind of what we're left with. Now, if you look at those numbers for the liquids, gasoline, alcohol, water, you can see, so let's look at ethanol, for example. Ooh, that's a favorite liquid of many people. So ethanol has an expansion of, about 1,100 parts per million, whereas glass, or ordinary glass, has an expansion of about 27 parts. So if you have a glass and it's full of ethanol, and the temperature goes up, what's going to happen? Well, the ethanol is going to spill over, right? Because the ethanol has quite a significant expansion, whereas the glass that it's sitting in is almost, it's almost negligible in comparison. Now with gases, they also put in a coefficient of volume expansion. I don't think that's so useful. Gases are more complicated because I can't directly relate temperature and volume without knowing something about pressure. Gases are easily compressed, so that means that, so we'll come back and look at what we call the ideal gas formula, the ideal gas model, to get a better idea of how to manage gases. Again, gases are going to be compressible, and that complicates this calculation. So let's look at an example with linear expansion. with thermal expansion. It says that we have a bridge. It's 200 meters long. The temperature is it's 200 meters long exactly at a temperature of 20 Celsius. And again, 20 Celsius is typically our reference. When we list all of these alphas here, it actually means that the alphas they're depending on us working from a reference temperature of 20 Celsius. Officially, that's how it works. Now, it turns out that if the temperature varies a little bit from that, it's not a big deal typically. But let's go ahead and we'll do the problem in terms of the reference temperature. And then we're going to say what happens to the length of the bridge of this piece of steel if we drop to minus 30. Hey, in the winter it could go to minus 30. And in the summer it could go to 40 Celsius, right? Here in the Bay Area we have such moderate temperatures all year round. We forget that in most places there are these much larger temperature swings during the course of the year, during the different seasons. So here's a piece of steel, 200 meters long. I looked up its expansion coefficient. It says it's 12 times 10 to the minus 6, which would mean I would have 12 parts per million of expansion for every degree Celsius. Now remember, kelvins are the same size units as Celsius. So I could actually do this in terms of per Kelvin. Anytime we have a formula in terms of delta T, that formula can be switched back and forth between Celsius and Kelvin. We don't have to add or subtract the 273s because we're only thinking in terms of temperature differences. All right, this is the formula that we first looked at, but there's another formula that goes along with it, which is at least as important, maybe more so, and that is we can sort out from this equation, well, how much does the length actually increase? And that's given by this portion multiplied by L naught. So the increase in length will be alpha L naught delta T, very important, make sure you have that to work from. And then here's a graph of what is the length of this object as a function of temperature. And the way the graph works is this. We can go up to use our reference temperature, 20 Celsius, and we measure this to be L naught, that's the 200 meter mark. And then as the temperature goes up, the length increases. As the temperature goes down, the length drops. And what we can do is we can collect data on materials and show that to a good approximation, those increases and decreases can be well represented with a linear function. So if we represent it as a linear function, if you remember your algebra for straight lines, I can do L minus L naught is equal to alpha L naught T minus T naught. That's a straight line that goes through the point L naught T naught and has a slope of alpha L naught. So that's where the formula is coming from. It's this assumption that a line will represent the expansions. And again, that works pretty well. If you're doing detailed engineering work with materials, you may be looking at thermal expansion formulas that indicate more detail as to exactly how that expansion, but at kind of the 0th level of approximation, we just assume the expansions and contractions are linear with respect to the temperature changes. So all that said, let's start plugging numbers in. At minus 30, that indicates a temperature difference, a temperature drop from our reference of 50 Celsius. I put all the numbers in. For the 200 meter piece of steel, that's 12 centimeters. Now 200 meters, that's big, right? That's like 2 soccer fields length or 2 football fields in length. And with this substantial temperature drop, I am seeing a contraction of 12 centimeters. So at first you might think, well, that's not a big deal. But if you're building a bridge or you're building a building and suddenly you've got an extra 12 centimeters in the structure, that can begin to cause problems. That can cause fractures within the material over time, the contraction and expansion. Similarly, I went up to the 40 Celsius. Now, that wasn't such an extreme this was only 20 Celsius above our reference temperature, and that led to an expansion of 4.8. So that's a good, I like this problem. It shows, how much contraction we might have in the winter months, how much expansion we could have in the summer months on this bridge. Okay, here's a kind of a standard conceptual question. If I have, let's start with the right. If I have a piece of aluminum or steel or something, and the temperature goes up, that's more kinetic energy. What happens to the distance between all of the nuclei within that block of aluminum or that block of steel, and all the neighboring nuclei move away from each other? Now that indicates that this entire piece will expand, but it also indicates that if I mark out any region inside of here, that also expands, right? Now what I can do is I can cut that out and repeat the process and go, same thing's going to happen. That portion that we cut out is going to get bigger. All right, those molecules are all going to move away from each other. If I look at all the nuclei lined up along the circle here, and they're all at some distance, all those distances go up. That opening is going to get bigger as the temperature goes up. So here's a problem we could look at. It says that we have a ring that has to fit over a rod. It says we have an iron ring, and we want that to fit a cylindrical iron rod. So let's see what that looks like. And we'll come back if we need to take a closer look at the numbers. So what this is in construction, this is what's called putting a rivet in. Now if I remember right, like the Eiffel Tower in Paris or something is entirely built with rivets. It's not welded. I could have this entirely wrong, so you better check. But the idea with rivets is what you can do is you can take one structural piece and you can, drill an opening inside there. And then you can take another piece of metal that's a little bigger. Now, it doesn't fit, but what you can do is you can either contract this, bring it down to a really low temperature, or you can expand this, either one, and so that temporarily at least, because of the temperature differences, the rivet will fit inside. And you can use that then when the temperature comes back so that they're both at the same temperature. Then you've got a really tight fit. You've got a piece of metal rivet in there that's too big to be there. And so this really clamps down tightly on the structure. And rivets, are used all over the place, and that's how we place the rivets. You can put a bunch of rivets in a bucket of dry ice, for example, brings them to a really low temperature. You can put the rivets in, they come back to normal temperature, and you have a good tight fit. It's unlikely someone's going to come up with a bucket of dry ice and contract the rivets. Anyway, so what they tell us in the problem is we're going to heat this up so that will fit. Now if I heat this up, all I really have to keep track of is the diameter. I don't have to do this problem in 2 dimensions. I don't have to do it in 3 dimensions. I can do it in 1 dimension and just say that 1 dimension is the diameter. If I can get the diameter here large enough so that this diameter fits, problem is solved. So what they tell us is the size of this is 6.445 centimeters currently. Now it says to make it fit, if I go back and read the problem, I hope I read this carefully, it says that we're going to have an additional 0.008 just to make sure that we can slide it in, right? So we want a little bit of extra diameter on this ring. So we're going to bump that up to 6.453. So it says this, it says, now, let's take a look at the ring now. The ring is currently at 20 Celsius, and its measured diameter is 6.420. Now we want to increase the temperature until that diameter is at 6.453. That means we need a delta L of 0.033. Very quick aside here. When we're doing these thermal expansion problems, notice how many significant figures we're keeping. And we kind of have to do that because we started with 4 significant figures each, but then we subtracted. And subtracting two numbers that are very similar to each other is very dangerous. We lose a lot of precision when that happens. So remember, that's the mantra for today, is subtraction is dangerous. All right, so that's the delta L. Now the temperature difference that we're going to need from our formula would be delta L over the expansion divided by the L naught. The L naught was 6.420, and the alpha value for the iron, the thermal coefficient of expansion, 12 parts per million per Celsius. So I put that in, put everything together, checked the units, and I intermittently went to kelvins, but then I went back to Celsius. Sorry about that. The delta T that I got was 428. Now the original temperature was 20 Celsius, so that says the temperature we have to get to is 448 Celsius. So that's a pretty high temperature that we're going to have to get the iron to, but that also means that when we put the rivet in and it cools back down to 20 Celsius, that's going to be a really nice tight fit, I hope. I'm not an engineer, so I don't know if that's going to fracture the iron. I hope not. But it should be a good tight fit. Another feature of thermal expansion you may be familiar with is sometimes if you have a jar that you just can't get open, sometimes it's too tight. So the jar lid has been put on very firmly. Now, one way to deal with that is to run a bunch of hot water over the jar lid. Now you might be thinking, yeah, but what about the glass? Doesn't the glass expand too? And what we saw in that chart is glass has a very low thermal expansion coefficient. Metals, and I'm assuming the lid is aluminum or steel, something like that, has a much higher expansion. So even if the glass heats up a bit, temperature goes up, we'll only get a little bit of thermal expansion. The metal will expand by a lot more, so as we go to higher temperatures, we can get the metal to expand, and that may solve the problem. Other times the problem, though, is that the object has been manufactured at one elevation and then it's been and there's a difference in air pressure, and so sometimes you can see that there's a reduced pressure inside, and that can be more complicated. So if it's been manufactured at high elevation but then brought to, back to ocean level, then there could be differences of pressure inside and out, and this can also help in those circumstances. But there could be a pressure difference you're dealing with too. Now, with volume expansion, this is what the formula looks like. Now, the volume expansion we said is going to be really handy for us in using liquids. Gases, not so much, because the gases expansion is also going to depend on pressure differences. Now, if you have the pressure remaining constant, then we can use those three-dimensional thermal expansions that we called beta, and we saw from the table, beta is roughly equal to 3 alpha. So let's see if we can slip one more example in before break here, maybe wrap things up with thermal expansion. Let's say that we have a gasoline tank, and we get some gasoline. The tank has 70 liters, and at the gas station it says, do not overfill, but we ignore the warnings and we overfill the tank. And so the gasoline is just completely filling our tank, and that's at 20 Celsius, and we intended to drive right away and use some of that gasoline, but instead we get delayed and the car gets parked out in the sun, and the gasoline in the tank end up going from 20 Celsius to 40 Celsius. Is that going to cause a problem? And we saw from the table of expansions that liquids tend to have a much higher expansion coefficient. So here is the thermal expansion coefficient for gasoline. It's 950 parts per million. Now for steel, the alpha was 12 parts per million, but remember, we're doing volumes here, so we got to use the beta value. That's 3 times alpha. That's 36 parts per million. That's nowhere near the expansion of the gasoline. I'm thinking we're in trouble. So here's the formula for the gasoline, or for the steel, and then the gasoline, we're using the same formula. Both V naughts are 70 liters. Now for the steel, what that's keeping track of is the volume inside the tank. But remember, as the temperature goes up, the entire tank is going to get bigger. So I can use the expansion of steel to represent how the empty volume within the steel tank increases. Putting those numbers in, I find that the steel increases by 0.05 liters, but the gasoline expansion is 1.33. That leaves us with 1.28 liters of gasoline. That isn't going to fit. It's going to spill out somehow. One thing to keep in mind here is, I think there's some homework problems to look at this. Water's expansion is complicated. It's not well represented by a linear function at familiar everyday temperatures, especially when we get down into the range between 0 and 10 Celsius, which is pretty common. Remember, as you get closer and closer to 0, water actually begins to expand. And once it turns to ice, it expands even more. So water's density, it's not linear. It's a more complicated function. Just something to be aware of. Remind yourself, water is complicated at temperatures between 0, and I'm going to say between 0 and 20 Celsius. Even in that range, using these linear thermal expansion coefficients aren't going to give us necessarily a reliable representation of what's happening with the water. So let's go ahead and stop there. So that takes us through thermal expansion. Let's take a break. We'll come back and take a look at gases. We said that the gases, for gases, we have to keep track of pressure, volume, and temperature all at the same time. Any questions at all, stop by. Let's take a look at the questions that you've got.